The second law of thermodynamics demands an absolute beginning, and infinite time is a logical fallacy that contradicts the most fundamental law in all of physics. Entropy, the measure of disorder, the count of microstates compatible with a given macrostate, quantified by Ludwig Boltzmann's formula S equals K sub B times the natural logarithm of W, increases in every isolated system. It never decreases spontaneously. It drives every irreversible process in the universe. Heat flows from hot to cold. Gases expand to fill their containers. Stars burn through their fuel, and ordered structures decay into disordered ones. The arrow of time, the unidirectional flow from past to future, from order to disorder, from low entropy to high entropy, is not a metaphor. It is a mathematical consequence of the second law, grounded in statistical mechanics and confirmed by every experiment in the history of thermodynamics. The Big Bang, the hot, dense origin of the observable universe, approximately 13.8 billion years ago, began in a state of extraordinarily low entropy, a state so special that Roger Penrose calculated its probability at approximately 1 in 10 to the power of 10 to the 123. And the heat death of the universe, the eventual state of maximum entropy, thermodynamic equilibrium, no free energy, no structure, no temperature gradients, is the predicted fate of a cosmos governed by the second law. If the universe had existed for infinite time, heat death would have already occurred. The fact that it has not, the fact that stars shine, temperature differences persist, and ordered structures exist, is empirical proof that time is not infinite. The universe had a beginning, and beginnings require causes. What follows is a forensic examination of the evidence, a cosmological argument grounded in the most fundamental laws of physics. By the end of this video, you will understand the second law of thermodynamics, not as an abstract principle, but as a measured, confirmed, inescapable law that governs every physical process. You will understand entropy and why it always increases. You will understand why an infinite past is thermodynamically impossible. Why a universe that has existed forever would be dead, featureless, and incapable of producing the structures we observe. You will understand why every attempt to escape this conclusion, steady-state models, cyclic universes, conformal cyclic cosmology, eternal inflation, the multiverse, fails when confronted with the second law. You will understand the Borde-Guth-Vilenkin theorem, which proves that any universe with an average expansion rate greater than 0 must have had a beginning. You will understand the past hypothesis, the requirement that the universe began in a state of extraordinarily low entropy, and why this initial condition is not explained by any known physics. And you will understand why the evidence, when examined honestly, points not to an eternal self-sustaining cosmos, but to a beginning and to a beginner. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us examine the evidence. The second law of thermodynamics is the most fundamental asymmetry in all of physics. It states that in any isolated physical system, total entropy never decreases. It can only increase or remain constant as the system evolves spontaneously. The law was formulated in the 1850s by Rudolf Clausius and Lord Kelvin. William Thomson, born 1824, died 1907, Irish-Scottish physicist, as a consequence of observations about heat engines. Heat flows spontaneously from hot bodies to cold bodies, never the reverse. No machine can convert heat entirely into work without some waste. No process can decrease the total entropy of an isolated system without external input. The mathematical statement is delta S is greater than or equal to 0. Delta S is the change in entropy of an isolated system. The inequality means entropy either stays the same in reversible idealized processes or increases in all real irreversible processes. This is not a statistical tendency that can be violated by rare fluctuations on cosmological timescales. For macroscopic systems, the probability of a spontaneous entropy decrease is so small that it has never been observed in any experiment and would not be expected to occur in the lifetime of the observable universe. Ludwig Boltzmann, born 1844, died 1906, Austrian physicist, the father of statistical mechanics, provided the microscopic foundation for the second law. Before Boltzmann, thermodynamics was a phenomenological science. It described what happened, heat flows from hot to cold, entropy increases, without explaining why. Boltzmann changed this by connecting thermodynamics to the microscopic behavior of atoms and molecules. He showed that entropy is not an abstract thermodynamic quantity imposed by fiat, but a measure of the number of microscopic configurations, microstates, compatible with a given macroscopic state. His formula, engraved on his tombstone in Vienna's Zentralfriedhof, a pilgrimage site for physicists, S equals K sub B times the natural logarithm of W. S is entropy. K sub B is Boltzmann's constant, approximately 1.381 times 10 to the negative 23 joules per Kelvin, named by Max Planck in honor of Boltzmann's statistical mechanics work, a conversion factor between the microscopic energy scale of individual molecules and the macroscopic temperature scale of thermometers and heat engines. W is the number of microstates, the number of distinct microscopic arrangements of particles that correspond to the same macroscopic properties: temperature, pressure, volume, total energy. The formula explains why entropy increases, and the explanation is not mysterious. It is mathematical. A low entropy state, an ordered, structured configuration, corresponds to a small number of microstates. Consider a room with all the air molecules in one corner. There is a limited number of ways to arrange the molecules such that they all fit in that corner, a limited W. A high entropy state, a disordered, uniform configuration with molecules spread throughout the room, corresponds to an enormously larger number of microstates. There are astronomically more ways to arrange the molecules uniformly than to confine them to one corner. When the system evolves randomly, when molecules collide, scatter, and exchange energy without any external direction, the system is overwhelmingly more likely to move toward a state with more microstates. The gas expands to fill the room, not because a force pushes it outward, not because nature wants uniformity, but because random molecular motion makes the expanded state overwhelmingly more probable. The second law is not a force. It is not a command. It is a statement about probability, about the statistical tendency of systems to evolve toward the most probable configuration. And the probability is so extreme, so overwhelming, so utterly one-sided, that it functions as an absolute prohibition on spontaneous entropy decrease in any macroscopic system. Think about that number W. For a gas of approximately 10 to the 23 molecules, a mole of gas, roughly the amount in a balloon, the number of microstates W for the equilibrium, uniform state, is a number so large that its logarithm is already of order 10 to the 23. The number of microstates corresponding to the gas being confined to 1/2 of its container is smaller by a factor that is itself a number with approximately 10 to the 23 digits in the exponent. The probability of the gas spontaneously returning to the confined state, all molecules simultaneously moving into 1/2 of the container, is the reciprocal of this factor. It is so small that it would not occur in 10 to the power of 10 to the 23 years, a timescale that makes the age of the universe, 13.8 billion years, approximately 10 to the 10 years, look like a rounding error. The second law is not approximate. For macroscopic systems, it is, for all practical and theoretical purposes, absolute. Boltzmann's work was controversial in his lifetime. Some physicists, notably Ernst Mach, rejected the atomic hypothesis entirely and considered Boltzmann's statistical approach philosophically suspect. Boltzmann suffered from depression and took his own life in 1906, before his ideas were universally accepted. Today, his formula is one of the most fundamental equations in all of physics, connecting the microscopic world of atoms to the macroscopic world of engines, stars, and universes. And the equation carries a devastating implication for any model of an infinite past. If W for the equilibrium state is enormously larger than W for the ordered states we observe, then the probability of the universe being in its current low entropy state after an infinite duration of entropy increase is 0. Not small, not negligible, 0. An infinite amount of time is more than sufficient for any system to reach equilibrium. The fact that the universe is not in equilibrium proves that an infinite amount of time has not passed. The past is finite. This is the first piece of evidence in the case for an absolute beginning. Arthur Eddington, born 1882, died 1944, British astrophysicist, Fellow of the Royal Society, the man who led the 1919 solar eclipse expedition that confirmed Einstein's general relativity by measuring the diffraction of starlight around the Sun, coined the phrase arrow of time to describe the unidirectional nature of physical processes. Eddington recognized something unsettling and deep. The arrow of time is unique among physical laws. Every other law of physics, Newton's laws of motion, Maxwell's equations of electromagnetism, the Schrödinger equation of quantum mechanics, Einstein's field equations of general relativity, is time-symmetric. These equations work equally well forward and backward. If you film the orbit of a planet and play the film in reverse, the reversed motion obeys the same equations. The laws of physics do not distinguish between past and future at the fundamental level. The second law of thermodynamics, though, does. The second law breaks the symmetry. It introduces a direction, a before and after, a past and future, a low entropy origin and a high entropy destination. A film of an egg shattering on a kitchen floor, played in reverse, the fragments leaping upward, the shell reassembling, the yolk reconstituting into a smooth, unbroken ovoid, looks immediately absurd. Not because the reversed process violates Newton's laws, it does not. Every individual molecular trajectory in the reversed film is physically valid, but because the reversed process violates the second law. The entropy of the shattered egg is higher than the entropy of the intact egg. The reverse process would decrease entropy. The second law forbids this for macroscopic systems. The arrow of time points in the direction of increasing entropy, from the intact egg to the shattered egg, from the ordered past to the disordered future, from the low entropy beginning to the high entropy end. Eddington stated with characteristic directness, "The law that entropy always increases holds, I think, the supreme position among the laws of nature." He went further. If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. The second law is not one law among many. It is, in Eddington's assessment, the supreme law, the law that governs the direction of time itself, the law that distinguishes past from future, the law that makes processes irreversible and history real. The arrow of time exists because the universe began in a state of low entropy. This is the past hypothesis, a term formalized by philosopher and physicist David Albert, born 1956, professor at Columbia University, which states that the early universe was in an extraordinarily special low entropy configuration. Without this hypothesis, the second law cannot explain the arrow of time. The second law tells us that entropy increases, but increases is a directional statement. It presupposes that there is a direction in which entropy is higher and a direction in which it is lower. It presupposes that the past had lower entropy than the present. And if we trace this logic backward, further and further into the past, the entropy must have been lower at earlier times. At the earliest time, at the Big Bang, approximately 13.8 billion years ago, approximately 4.35 times 10 to the 17 seconds, approximately 8.68 times 10 to the 17 half seconds, the entropy must have been at or near its minimum value compatible with the universe's total energy. The past hypothesis is not a derivation. It is not a prediction of any known theory. It is not a consequence of general relativity, quantum mechanics, the Standard Model, or any proposed theory of quantum gravity. It is an assumption, a boundary condition imposed on the initial state of the universe. Every calculation in thermodynamics and statistical mechanics that involves the arrow of time assumes the past hypothesis. Without it, there is no thermodynamic arrow. Without the thermodynamic arrow, there is no distinction between past and future. Without a distinction between past and future, there are no causal chains, no history, no processes, no life, no science. The past hypothesis is the foundation of the arrow of time, and it is assumed, not explained. This is the question that the second law forces us to confront. Why was the initial entropy so low? Why did the universe begin in such an extraordinarily special state? The answer is not found in physics. Physics tells us that entropy increases from a low entropy initial state. It does not tell us why the initial state was low entropy. It does not derive the initial conditions from first principles. It does not explain why the boundary condition has the specific character it does. The question is not about the dynamics. The dynamics are well understood. The question is about the boundary. And the boundary is where physics ends and metaphysics begins. Roger Penrose, born 1931, British mathematician and physicist, Rouse Ball Professor of Mathematics at Oxford, Nobel Prize in Physics 2020 for demonstrating that black hole formation is a firm prediction of general relativity, quantified the specialness of this initial state with a calculation that has become one of the most cited numbers in the fine-tuning literature. Penrose asked, if the universe's initial state were drawn randomly from the space of all possible initial configurations compatible with its total energy, what is the probability that it would be the specific low entropy state we observe? His answer is approximately 1 in 10 to the power of 10 to the 123. Let us attempt to comprehend this number, knowing in advance that the attempt will fail. 10 to the 123 is a number with 123 digits. It exceeds the number of particles in the observable universe, approximately 10 to the 80, by a factor of 10 to the 43. But Penrose's number is not 10 to the 123, it is 10 to the power of 10 to the 123, a tower of exponents, a double exponential. 10 to the power of 10 to the 123 is a number that cannot be written in standard decimal notation. To write it out, to write a 1 followed by 10 to the 123 zeros, you would need a sheet of paper with 10 to the 123 digits. If each digit occupied 1 Planck length, approximately 1.616 times 10 to the negative 35 meters, approximately 6.36 times 10 to the negative 34 inches, the smallest meaningful length in physics, the number would stretch across a distance of approximately 10 to the 88 meters, a distance that exceeds the diameter of the observable universe, approximately 8.8 times 10 to the 26 meters, by a factor of 10 to the 61. The number is not large. It is beyond large. It is beyond the capacity of physical reality to contain its representation. Penrose called this initial state absurdly unlikely to occur by chance. He is not a theist. He does not draw the theistic conclusion publicly. But the number he calculated is a datum, and the datum demands an explanation. What kind of explanation? Not a scientific explanation. No equation within physics derives this number. Not a probabilistic explanation. The probability is so small that invoking chance is not an explanation, but a refusal to explain. Not a naturalistic explanation. Every naturalistic alternative, multiverse, cyclic cosmology, quantum fluctuation, either fails on its own terms or merely pushes the same question back one level. The only explanation that addresses the datum directly is deliberate configuration. The initial conditions were chosen, selected, specified by an agent with knowledge of the alternatives and the power to instantiate a specific one. Before I continue, consider what this means. Take a moment. The initial state of the universe, the state from which everything we observe emerged, had a probability of occurring by chance of approximately 1 in 10 to the power of 10 to the 123. Every star in the sky, every element on the periodic table, every molecule of water in every ocean, every strand of DNA in every living cell, every thought in every mind, all of it traces back to a single, specific, low-entropy initial state whose probability of random occurrence is this number. And this number is not derived from theology. It is derived from statistical mechanics, from Boltzmann's formula, applied to the gravitational degrees of freedom of the early universe, by one of the most distinguished mathematicians of the 20th and 21st centuries. The number is physics. The conclusion it demands is metaphysics. But the conclusion is rational, because the physics leaves no naturalistic alternative standing. This is the part that stays with me, not the scale, the precision. The universe did not begin in a random state. It began in the most special state compatible with its dynamics, a state whose probability of random occurrence is beyond the capacity of physical reality to represent, beyond the capacity of mathematics to visualize, and beyond the capacity of any naturalistic explanation to account for. Precision of this magnitude does not arise from randomness. It arises from decision. Decision requires knowledge. Knowledge requires mind. Mind requires a being that possesses mind, not unconscious matter, not blind forces, not quantum fluctuations in a pre-existing vacuum. A being, an intelligence, a creator. This brings us to Lord Kelvin's argument, the argument from heat death, and to the logical impossibility of an infinite past. In 1852, Lord Kelvin, William Thomson, born 1824, died 1907, published a paper arguing that the second law of thermodynamics implied a universal tendency in nature to the dissipation of mechanical energy. Kelvin recognized what others had not yet articulated. If the second law applies to the universe as a whole, if the cosmos is an isolated system in which entropy always increases, then the universe is running down. Temperature differences are equilibrating. Free energy is being consumed. Ordered structures are decaying. And the endpoint, the inevitable final state, is thermodynamic equilibrium, a condition of maximum entropy in which no temperature differences exist, no free energy is available, and no macroscopic processes can occur. Kelvin called this the heat death of the universe, a phrase that has since entered both scientific and philosophical discourse. Kelvin went further. He argued that if the universe had existed for infinite time, if there were no beginning, if the cosmos had always been here, then the heat death should have already occurred. An infinite duration is sufficient for any finite rate of entropy increase to bring the system to equilibrium. If entropy has been increasing for an infinite number of years, it should have reached its maximum an infinite time ago. The universe should be dead, cold, featureless, at uniform temperature, with no stars, no galaxies, no temperature gradients, no life, no processes of any kind. The universe, though, is not. The universe is manifestly not in thermodynamic equilibrium. The cosmic microwave background, discovered in 1965 by Arno Penzias and Robert Wilson at Bell Labs in Holmdel, New Jersey, earning them the Nobel Prize in Physics in 1978, has a temperature of approximately 2.725 Kelvin. This is not zero. The CMB is an almost perfect black-body spectrum, confirmed by Kobe's FIRAS instrument to extraordinary precision. But the CMB also has tiny anisotropies, temperature variations of approximately 1 part in 100,000 that represent density fluctuations in the early universe. These fluctuations seeded the formation of galaxies, clusters, and the entire large-scale structure of the cosmos. The universe is structured. It has temperature differences ranging from 2.7 Kelvin in intergalactic space to tens of millions of degrees in the cores of stars. It has gravitational potential energy stored in galaxy clusters. It has nuclear binding energy stored in hydrogen fuel. It has an enormous reservoir of free energy that is being consumed slowly, steadily, irreversibly as entropy increases. The fact that free energy remains, the fact that stars are still shining, that hydrogen is still available for fusion, that the universe has not yet reached heat death, is direct observational evidence that the universe has not existed for infinite time. The argument is deductive, the premises are empirical, and the conclusion is inescapable. Premise 1. In an isolated system, entropy always increases. The second law, confirmed by every experiment in thermodynamics. Premise 2. If a system has existed for infinite time, entropy has had infinite time to increase and would have reached its maximum. Logical consequence of premise 1 applied over infinite duration. Premise 3. The universe is not at maximum entropy. Observational fact: stars shine, structure exists, temperature differences persist, free energy is available. Conclusion: the universe has not existed for infinite time. The past is finite. The universe had a beginning. What would you conclude from this evidence if you followed it honestly? The logic is valid. The premises are confirmed. The conclusion follows necessarily. The only way to escape the conclusion is to deny one of the premises, to deny the second law, to deny that infinite time is sufficient for equilibrium, or to deny that the universe is not in equilibrium. No serious physicist denies any of these. The conclusion stands. The universe had a beginning. This brings us to the alternative models, the attempts to escape this conclusion, and to the specific ways in which each one fails. The steady-state model, proposed by Hermann Bondi, Thomas Gold, and Fred Hoyle in 1948, offered an eternal universe with no beginning. In the steady-state model, the universe expands, but new matter is continuously created to maintain a constant average density. The universe looks the same at all times. There is no privileged moment, no origin, no creation event. The model was explicitly designed to avoid the theological implications of a Big Bang. Let us examine this claim fairly. The steady-state model has a certain philosophical elegance. It avoids the question, what came before, by positing that there was no before. The universe simply is, has always been, and will always be. But the model faces two fatal problems. First, observational evidence. The discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson at Bell Labs, a uniform thermal radiation at approximately 2.725 Kelvin filling all of space, was decisive. The CMB is a relic of a hot, dense early state, exactly as the Big Bang predicted. An eternal, unchanging universe would not produce such a relic. The CMB was the observational death blow to the steady-state model, and the model has been largely abandoned since. COBE, NASA's cosmic background explorer, operating from 1989 to 1993, confirmed that the CMB is a near-perfect black-body spectrum and detected anisotropies of approximately 1 part in 10 to the 5. WMAP and Planck refined these measurements to extraordinary precision. The observational case for a hot Big Bang origin is overwhelming. Second, thermodynamics. Even if the observational evidence were ambiguous, the steady-state model would still face the second law. An eternal, continuously creating universe would accumulate entropy without limit. The continuous creation of matter, low entropy matter injected into an expanding space, would require a mechanism to maintain low entropy indefinitely. No such mechanism exists in the steady-state model. No known physics provides one. The model simply asserts that matter appears, without specifying how the newly created matter has low enough entropy to sustain an arrow of time over infinite duration. The steady-state model does not solve the entropy problem. It ignores it. The verdict? The steady-state model is observationally falsified and thermodynamically incoherent. It fails. This brings us to cyclic models, the oscillating universe, and to an argument that dates to 1934. The oscillating universe, proposed in its modern form by Alexander Friedmann in 1922, who showed that Einstein's field equations permit expanding and contracting solutions, and analyzed thermodynamically by Richard Tolman in 1934 in his book Relativity, Thermodynamics and Cosmology, suggests that the universe undergoes an infinite sequence of expansions and contractions. Each expansion reaches a maximum size, then reverses under gravitational attraction, contracting back to a hot, dense state, a big crunch. At the crunch, the universe bounces, the contraction reverses into a new expansion, a new Big Bang, and the cycle repeats. The universe has no beginning and no end. It cycles forever. The appeal is clear. If the universe is eternal, there is no first moment, no creation event, No need for an external cause. The question, what caused the Big Bang, is dissolved. The Big Bang was caused by the preceding Big Crunch, which was caused by the preceding expansion, and so on without limit. The oscillating universe is the materialist's ideal. An eternal, self-contained, causally closed system that requires no external explanation. Tolman, though, identified the fatal problem and published it in 1934 in his book Relativity, Thermodynamics and Cosmology. The problem is entropy. Each cycle of the oscillating universe involves irreversible processes: star formation, nuclear fusion, gravitational collapse, electromagnetic radiation, particle production, black hole formation. These processes increase entropy. The second law holds within each cycle, and the entropy accumulated during one cycle does not disappear at the bounce. There is no known mechanism, no law of physics, no principle of thermodynamics that would reset entropy to a lower value at the transition from crunch to bounce. The entropy carries over. The consequence is precise and devastating. Each successive cycle begins with higher entropy than the last. Higher entropy means more disorder, more uniform temperature, less free energy, less capacity for structure formation. And higher entropy at the start of a cycle means a longer cycle, because the expansion must reach a larger maximum size before gravity can reverse it and the contraction takes longer. Tolman showed that each cycle is longer and larger than the previous one. The cycles are not identical. They are asymmetric, growing progressively larger, progressively more disordered, progressively closer to thermodynamic equilibrium. If the cycles have been going on for an infinite number of iterations, the accumulated entropy would be infinite. The universe would be in thermodynamic equilibrium. The current cycle would be infinitely large, infinitely disordered, with no free energy and no capacity for structure. But we observe the opposite: a finite-sized, structured, low-entropy universe with abundant free energy. Therefore, the cycles have not been going on forever. There was a first cycle, a beginning, and that beginning requires a cause. Modern cyclic models attempt to evade Tolman's objection with various mechanisms. The ekpyrotic model, proposed by Paul Steinhardt and Neil Turok, replaces the Big Crunch with a collision between higher dimensional membranes, branes, in a five-dimensional spacetime. The collision is not a singularity, but a smooth transition, and the proponents claim that the collision can produce a low-entropy, homogeneous initial state for the new cycle. But the claim is not demonstrated. No mechanism has been shown to decrease the total entropy of an isolated system. The brane collision may produce a locally smooth region, but the total entropy of the system, including the higher dimensional bulk, must still obey the second law. The fine-tuning is not eliminated. It is relocated to the properties of the branes, the potential energy of the collision, and the dynamics of the extra dimensions, none of which is observed or independently constrained. Penrose's conformal cyclic cosmology, CCC, proposed in 2002, takes a different approach. Penrose accepts that the universe will eventually reach heat death. After all massive particles have decayed, protons, neutrons, electrons, and all black holes have evaporated through Hawking radiation, the quantum mechanical process by which pairs of virtual particles near the event horizon produce a slow outward flux of radiation, first described by Stephen Hawking in 1975, the universe will consist only of massless particles, photons and gravitons. For massless particles, there is no intrinsic timescale. No clock can be constructed from massless particles alone. Penrose proposes that this featureless, massless state can be conformally rescaled, mathematically stretched into a new Big Bang, initiating a new eon. The old eon's heat death becomes the new eon's Big Bang. The cycle repeats. CCC is mathematically inventive, but it faces severe challenges. First, it requires that all massive particles eventually decay, including protons. The current experimental lower bound on the proton lifetime from the Super Kamiokande detector in Japan is approximately 10 to the 34 years. No proton decay has been observed. If protons do not decay, CCC's premise fails. Massive particles persist. Conformal symmetry does not hold, and the conformal rescaling cannot be performed. Second, the conformal mapping that connects one eon to the next is a mathematical operation, not a physical process. There is no known mechanism in nature that performs a conformal rescaling of space-time. The mapping is a coordinate transformation on paper, not a physical event that occurs in the cosmos. CCC is a mathematical model, not a physical theory in the usual sense. Third, and most fundamentally, CCC does not explain the first eon. Even if the cyclic structure works, the chain of eons does not extend infinitely into the past without a thermodynamic cost. Each eon's information is, in Penrose's framework, erased by the conformal stretching. But the total entropy of the system across all eons, if it can be meaningfully defined, either increases, violating the assumption that CCC avoids entropy accumulation, or requires a first eon with specific initial conditions that are themselves unexplained. CCC does not derive its starting point, it assumes it. And the starting point, the first eon, with its specific laws and initial conditions, is a beginning that requires explanation. This brings us to cosmic inflation, and to the theorem that closes the final escape route. Alan Guth, born 1947, American physicist at MIT, proposed cosmic inflation in 1980, published in 1981. Inflation posits a brief period of exponential expansion, an expansion by a factor of at least 10 to the 26 in linear dimensions, occurring in approximately 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, driven by the potential energy of a scalar field, the inflaton. The inflaton field begins in a high-energy false vacuum state and decays to a lower-energy true vacuum, releasing enormous energy that drives the exponential expansion. Inflation was a theoretical triumph. It solved three long-standing problems in Big Bang cosmology with a single mechanism. The horizon problem. why the cosmic microwave background has almost exactly the same temperature in all directions, even in regions of the sky that were never in causal contact, never able to exchange signals at the speed of light, in the standard Big Bang model. Inflation solves this by proposing that all observable regions were in causal contact before inflation, and the exponential expansion stretched this initially connected region to a size far larger than the observable universe. The flatness problem. Why the spatial geometry of the universe is so extraordinarily close to flat. Omega approximately equals 1, as measured by Planck, to within 0.2%. In the standard Big Bang, even a tiny deviation from flatness early on would be amplified by the subsequent expansion, requiring the initial density to be fine-tuned to many decimal places. Inflation solves this by driving the geometry toward flatness, regardless of the initial curvature, through the exponential expansion. And the monopole problem. Why magnetic monopoles, predicted by grand unified theories of particle physics, are not observed. Inflation dilutes any monopoles produced before or during the inflationary epoch to undetectable densities. Inflation is supported by observational evidence. The Planck satellite confirmed the flat geometry, the nearly scale-invariant spectrum of primordial density fluctuations, spectral index n sub s approximately equals 0.965, and the Gaussian statistics of the CMB anisotropies, all predictions of inflationary models. WMAP, the Wilkinson Microwave Anisotropy Probe, NASA 2001 to 2010, determined the age of the universe at approximately 13.77 billion years, and the composition, approximately 5% normal matter, 27% dark matter, 68% dark energy. The observational support for inflation is strong. Inflation, though, does not solve the entropy problem. Sean Carroll, born 1966, American cosmologist, atheist, professor at Johns Hopkins, has acknowledged that inflation itself requires fine-tuned initial conditions. The inflaton field must begin in a specific low-entropy, high-potential energy state for inflation to occur. If the initial state of the inflaton were random, drawn from a uniform distribution over possible field configurations, inflation would be extraordinarily unlikely. Carroll has written that the initial state required for inflation is itself a fine-tuned state that demands explanation. Inflation does not explain why the early universe had low entropy. It assumes a low-entropy inflaton configuration and then explains how that configuration produces the flat, homogeneous universe we observe. The fine-tuning problem is not solved. It is pushed back one level. Andrei Linde, born 1948, Russian-American physicist at Stanford, developed eternal inflation, in which the inflationary expansion never ends globally. Different regions of space-time exit inflation at different times, producing bubble universes, each with potentially different physical properties. In eternal inflation, our observable universe is just one bubble in an infinite, ever-inflating space. The multiverse. In 2003, though, Arvind Borde, Alan Guth, and Alexander Vilenkin proved a theorem that placed a hard, model-independent limit on all inflationary models, including eternal inflation. The Borde-Guth-Vilenkin theorem, BGV theorem, states any spacetime region in which the average expansion rate is greater than 0, the average Hubble parameter, time averaged over the region's history is positive, must be geodesically past incomplete. In physical terms, it must have had a beginning. The theorem is notable for its generality. It does not assume a specific theory of gravity. It does not assume homogeneity or isotropy. It does not assume the Einstein field equations. It does not assume any particular energy condition. It applies to any spacetime, regardless of the matter content, regardless of the geometry, regardless of the number of spatial dimensions in which the time-averaged expansion rate is positive. The only assumption is that, on average, the universe, or multiverse region, has been expanding. And since all observations confirm that the universe is expanding, confirmed by Hubble's 1929 observations of galactic redshifts, by WMAP's precision measurements, by Planck's data, by supernova observations, the BGV theorem applies. The Hubble law, V equals h sub 0 times d, where V is the recession velocity of a galaxy, h sub 0 is the Hubble constant, approximately 67 to 68 kilometers per second per megaparsec from Planck, and d is the distance, is the empirical expression of this expansion. Edwin Hubble, born 1889, died 1953, American astronomer, discovered in 1929 that distant galaxies are receding from us, with recession velocities proportional to their distances. This was the first observational evidence for the expansion of the universe. The 1998 supernova observations by the teams of Saul Perlmutter, Brian Schmidt and Adam Rees, who shared the 2011 Nobel Prize in Physics, showed that the expansion is accelerating, driven by dark energy. The expansion rate, h, is positive. It has been positive for the entire observable history of the universe. The BGV theorem applies. Alexander Vilenkin stated the implication with characteristic clarity. It is said that an argument is what convinces reasonable men, and a proof is what it takes to convince even an unreasonable man. With the proof now in place, cosmologists can no longer hide behind the possibility of a past eternal universe. There is no escape. They have to face the problem of a cosmic beginning. The Friedmann equation, the master equation of cosmological expansion, derived by Alexander Friedmann in 1922 from Einstein's field equations, governs the dynamics. H squared equals 8 pi g over 3 times rho minus k over a squared plus lambda over 3. H is the Hubble parameter. G is the gravitational constant. Rho is the total energy density. K is the spatial curvature parameter, 0 for a flat universe, as Planck confirms. A is the scale factor tracking the expansion. Lambda is the cosmological constant representing dark energy. With positive rho and positive lambda, as observed, H is positive. The BGV theorem states that if the time-averaged H is positive, the spacetime is past incomplete. It had a beginning. I return to this point often, not because it is comfortable, because it is true. The BGV theorem is not a theological argument. It is a mathematical proof within the framework of general relativity and cosmological kinematics. It was proved by 3 physicists, Borde, Guth, and Vilenkin, none of whom is a theist. Guth is the inventor of inflation. Vilenkin has written extensively about the multiverse. They proved their own model's limitation. Even eternal inflation had a beginning. The past is finite. The escape route through eternal inflation is closed by the physicists who built it. I return to this point often, not because it is comfortable, because it is true. The Borde-Guth-Vilenkin theorem is not a theological argument. It is a mathematical proof within the framework of general relativity. It applies to any expanding spacetime, and it concludes, the past is finite. There was a first moment. There was a beginning. And the question of what caused that beginning is not a scientific question, it is a metaphysical question that science cannot answer, but the evidence demands. This brings us to the heat death, the eventual fate of a universe governed by the second law, and to what it implies about the present. The heat death of the universe is not a dramatic cosmic catastrophe. It is not an explosion. It is not a collapse. It is the opposite. The ultimate absence of drama, the terminal quieting of all processes, the final exhaustion of every gradient that makes anything happen anywhere. In a universe dominated by dark energy, as ours is, with approximately 68% of its total energy density in the form of vacuum energy, confirmed by the 1998 supernova observations and the Planck satellite data, the expansion accelerates. Every galaxy cluster becomes an isolated island, drifting away from every other cluster at speeds that eventually exceed the speed of light. Not because the galaxies move through space faster than light, but because space itself expands between them faster than light can cross it. The cosmic horizon shrinks. Galaxies that were visible a billion years ago redshift out of view, their light stretched to wavelengths longer than the observable universe, effectively vanishing from any observer's sky. Within each isolated galaxy cluster, stars continue burning, but not forever. The Sun, a G-type main sequence star with approximately 5 billion years of fuel remaining, will exhaust its hydrogen core, swell into a red giant engulfing Mercury, Venus, and possibly Earth, then shed its outer layers as a planetary nebula, a shell of glowing gas, iridescent in ultraviolet and visible light, expanding into the interstellar medium, leaving behind a white dwarf, approximately the size of Earth, but with a mass of approximately 0.6 solar masses. The white dwarf will cool, slowly, over trillions of years, from an initial surface temperature of approximately 100,000 Kelvin to a cold, dark, crystallized sphere. A black dwarf. No light, no heat, no radiation. A dead cinder drifting through an expanding void. More massive stars end differently, as neutron stars or black holes. Neutron stars, approximately 20 kilometers, 12 miles in diameter, with densities of approximately 10 to the 17 kilograms per cubic meter, a teaspoon of neutron star material weighing approximately 6 billion tons, cool over billions of years. Black holes persist longer. A solar mass black hole evaporates through Hawking radiation, the quantum mechanical process by which pairs of virtual particles near the event horizon produce a slow outward flux of radiation, on a timescale of approximately 10 to the 67 years. A supermassive black hole at the center of a galaxy with a mass of billions of solar masses evaporates on a timescale of approximately 10 to the 100 years. 10 to the 100 years, a googol of years, a number with 100 digits. After the black holes evaporate, after the last Hawking photon drifts into an expanding void of near absolute zero temperature, what remains? Photons, neutrinos, gravitons, massless or nearly massless particles spread across a volume of space so vast that the distance between any two particles exceeds the observable universe of today. No structures, no gradients, no processes, no clocks, because time requires change and there is nothing left to change. The temperature approaches but never quite reaches absolute zero. The entropy is at its maximum. The universe is dead. The Bekenstein-Hawking entropy formula quantifies the entropy of black holes. S sub BH equals K sub BC cubed A over 4 GH bar. S sub BH is the entropy of the black hole. K sub B is Boltzmann's constant. C is the speed of light, approximately 299,792 kilometers per second. Approximately 186,282 miles per second. A is the area of the event horizon, the boundary of no return, the surface inside which the escape velocity exceeds the speed of light. G is the gravitational constant, approximately 6.674 times 10 to the negative 11 cubic meters per kilogram per second squared. H bar is the reduced Planck constant. The formula, developed by Jacob Bekenstein in 1973, building on earlier work by John Wheeler and Stephen Hawking in 1975, was one of the most surprising results in theoretical physics. It showed that black holes are not information-free voids, but thermodynamic objects with temperature and entropy. A solar mass black hole has an entropy of approximately 10 to the 77 in natural units, far greater than the entropy of the star that collapsed to form it. Supermassive black holes have correspondingly enormous entropies. The total entropy of the observable universe, including all black holes, is estimated at approximately 10 to the 104. At the Big Bang, the entropy was approximately 10 to the 88 from the CMB photons alone, lower by a factor of 10 to the 16. This gap from 10 to the 88 at the Big Bang to 10 to the 104 today is the thermodynamic distance the universe has traversed since its beginning. It is not at the end. It is not at equilibrium. It is between the beginning and the heat death. And the fact that it is between, not at the destination, not at maximum entropy, not at thermodynamic equilibrium, proves that the time elapsed since the beginning is finite. An infinite amount of time would have closed the gap. The gap persists. The past is finite. Now let us examine the materialist responses to this evidence and apply the prosecution after defense model to each. The first materialist response: perhaps quantum fluctuations can reverse entropy, allowing an eternal universe to periodically reset itself. Let us examine this claim with precision. Quantum fluctuations are real. They are brief, constrained energy excursions permitted by the Heisenberg uncertainty principle, delta E times delta T greater than or equal to h bar over 2, virtual particles appear and annihilate in the vacuum. But quantum fluctuations do not reverse the second law for macroscopic systems. The second law is a statistical statement. For systems with more than a few dozen particles, the probability of a spontaneous entropy decrease is so small that it has never been observed and would not be expected to occur in the lifetime of the observable universe. For a macroscopic system, say a gas of 10 to the 23 molecules, the probability of all molecules spontaneously concentrating in one corner of their container is approximately 1 in 10 to the power of 10 to the 23. For the entire observable universe, approximately 10 to the 80 particles, the probability of a spontaneous entropy decrease large enough to reverse cosmic heat death is a number so small that it cannot be meaningfully written. Even if such a fluctuation occurred, in some fantastically unlikely scenario, it would not produce the ordered universe we observe. This is the Boltzmann brain paradox, identified by physicists as a fatal problem for any model of an equilibrium universe. The paradox is this. In a universe at thermodynamic equilibrium, random fluctuations occasionally produce regions of low entropy. Some of these regions contain ordered structures, galaxies, stars, planets. But the vast majority of fluctuations that produce an observer, an entity capable of making observations and forming memories, do not produce an entire ordered universe. They produce the minimum fluctuation necessary for observation. A single brain floating in a void with false memories of a universe that never existed. A Boltzmann brain. The probability of a random fluctuation producing a Boltzmann brain is astronomically higher than the probability of a fluctuation producing an entire ordered universe with 13.8 billion years of consistent history, billions of galaxies, and a coherent cosmic microwave background. If the universe were eternal and in equilibrium, with occasional random fluctuations producing pockets of order, we should expect to be Boltzmann brains, momentary observers with false memories, not inhabitants of a vast, ancient, structured cosmos with a consistent physical history. The fact that our observations are consistent with a real cosmic history, that the CMB matches theoretical predictions, that galactic development follows expected patterns, that the elements have the abundances predicted by Big Bang nucleosynthesis, is evidence that we are not Boltzmann brains. And if we are not Boltzmann brains, then the universe is not an eternal equilibrium state with random fluctuations. The past is finite. The low entropy is primordial, a feature of the initial conditions, not a random fluctuation. The Boltzmann brain paradox is not a curiosity. It is a rigorous physical argument against an infinite past. Sean Carroll has discussed this paradox extensively, acknowledging that any cosmological model that predicts more Boltzmann brains than real observers is empirically self-defeating, because the model's own predictions undermine the reliability of the observations used to support it. An eternal equilibrium universe produces vastly more Boltzmann brains than real observers. Therefore, an eternal equilibrium universe is empirically self-defeating. The conclusion? The universe is not eternal. It had a beginning. The low entropy is a boundary condition, not a fluctuation. The second materialist response. The multiverse explains why our universe has low entropy and fine-tuned constants. We simply happen to exist in a life-friendly pocket. Let us apply the prosecution model. The defense? The multiverse, the ensemble of bubble universes produced by eternal inflation, contains an infinite number of regions with varying properties. We observe the properties we do because only those properties permit observers to exist. No designer needed, just probability across infinite trials. The cross-examination. The multiverse has zero observational evidence. No other universe has been observed, measured, or detected. No experiment has been proposed that could test the existence of other universes. The theory is unfalsifiable. No possible observation could prove it wrong. And the BGV theorem applies to the multiverse as well. Any region with average expansion greater than zero must have had a beginning. The multiverse is not past eternal. It had a beginning, and that beginning requires a cause. The multiverse also does not explain why the laws of physics that govern the multiverse have the specific form they do. The inflationary mechanism itself requires fine-tuned initial conditions, as Carroll acknowledges. The multiverse pushes the fine-tuning problem back one level, from why are our constants fine-tuned to why do the multiverse-generating laws have the specific form that produces fine-tuned universes? The problem is not solved, it is multiplied. The prosecution. The multiverse is not science. It is philosophical speculation invoked to avoid the conclusion that fine-tuning implies a fine-tuner. It violates the principle of parsimony. Instead of one universe requiring explanation, it posits an infinite number of unobservable universes. It does not explain the origin of the laws governing the multiverse. It does not explain the initial conditions of the multiverse. And it is passed incomplete by the BGV theorem. The multiverse is not an escape from a beginning. It is a beginning concealed behind infinite speculation. The verdict? The multiverse fails as an explanation. The evidence still points in one direction. The third materialist response. Science will eventually explain the initial conditions and the low entropy of the Big Bang. Let us examine this. We don't know yet, but science will figure it out is not an argument. It is a statement of faith. Faith in the capacity of future discoveries to resolve a question that may lie beyond the scope of empirical science. The past hypothesis. The requirement that the universe began in a low entropy state is not a derivable result within any known framework of physics. It is a boundary condition, an assumption about the initial state of the universe that is imposed, not derived. No equation in physics generates the initial conditions from more fundamental principles. The Friedmann equation describes how the universe evolves given initial conditions. It does not derive the initial conditions. The second law describes how entropy increases given a starting point. It does not explain why the starting point has low entropy. Science describes how systems evolve within a framework of laws. It cannot explain why the framework exists or why the initial conditions are what they are. The question, why was the initial entropy so low, is not a physics question that awaits a future equation. It is a question about the existence and character of the boundary conditions. And boundary conditions are, by definition, outside the scope of the dynamics they constrain. Promising that science will explain it is faith in a future that may never arrive, deployed to avoid a present conclusion that the evidence supports. Some questions are not scientific questions. Science can describe how the universe operates, how entropy increases, how space-time expands, how galaxies form from primordial density fluctuations. It cannot answer why anything exists rather than nothing. It cannot explain why the second law holds, why entropy increases rather than decreasing or remaining constant or fluctuating randomly. It cannot explain why the initial conditions were so extraordinarily special. It cannot explain why the physical constants have the specific values they do, why the fine structure constant is approximately 1 over 137, why the cosmological constant is approximately 10 to the negative 122 in Planck units, why the proton-to-electron mass ratio is approximately 1836. The fine structure constant, alpha equals e squared over 4 pi epsilon sub 0 h bar c, is a dimensionless number that determines the strength of the electromagnetic interaction. If alpha were a few percent larger, stellar nucleosynthesis would fail. If it were a few percent smaller, stable atoms would not form. The value is measured to extraordinary precision by atomic clock experiments at NIST, stable to parts in 10 to the 17 over years, confirming that this fine-tuning is not a local, temporary anomaly, but a persistent feature of the laws. The Planck mass, m sub p, equals the square root of h bar c over g, sets the natural mass scale from fundamental constants. Its value is approximately 2.18 times 10 to the negative 8 kilograms, approximately 4.81 times 10 to the negative 8 pounds. The proton mass is approximately 10 to the negative 19 times the Planck mass, a ratio of roughly 10 to the 19 to 1. Why this ratio? No theory derives it. It is a measured fact. And if it were different by modest factors, nuclear physics would not produce the stable nuclei that constitute ordinary matter. The hierarchy problem. The question of why the electroweak scale is so much smaller than the Planck scale is one of the deepest unsolved problems in particle physics. It is a fine-tuning problem at its core. The 1998 supernova observations by the teams of Saul Perlmutter, Brian Schmidt and Adam Rees, who shared the 2011 Nobel Prize in Physics, showed that the expansion of the universe is accelerating, driven by dark energy. Dark energy constitutes approximately 68% of the universe's total energy density. Its effect is to increase the rate of entropy production in the far future, accelerating the approach to heat death. The discovery confirmed that the universe has a thermodynamic fate: eventual equilibrium, maximum entropy, no free energy, no structure. The accelerating expansion means that the heat death is not merely a distant possibility, but the inevitable conclusion of cosmic thermodynamics. The second law wins. Entropy always increases, and the universe moves inexorably toward its end. The Higgs boson discovery at the Large Hadron Collider in 2012, at a mass of approximately 125 giga-electron volts, confirmed the Standard Model's last missing piece, and raised further fine-tuning questions. The Higgs mass appears to place our universe near the boundary between a stable vacuum and a metastable vacuum, a configuration that seems just right for complex chemistry without vacuum instability. This is another datum in the fine-tuning evidence. The Higgs mass is not derived from first principles. It is measured, and its value permits the physics that permits structure. LIGO's detection of gravitational waves from merging black holes in September 2015, the first direct detection, confirming Einstein's century-old prediction, demonstrated that black holes are real astrophysical objects that merge, radiate gravitational energy, and increase the entropy of the universe. Each black hole merger increases the total entropy. The Bekenstein-Hawking entropy of the final black hole exceeds the sum of the entropies of the two initial black holes. Black holes are the dominant contributors to cosmic entropy. The total entropy of the observable universe is estimated at approximately 10 to the 104 in natural units, with the vast majority residing in supermassive black holes. At the Big Bang, the entropy was far lower, approximately 10 to the 88 from CMB photons. The gap, from 10 to the 88 to 10 to the 104, measures how far the universe has moved along its thermodynamic trajectory. It is not at the end, it is between the beginning and the end. And the fact that it is between proves that the beginning was recent, not infinitely long ago. Voyager 1's crossing of the heliopause in 2012, after 35 years of travel at approximately 17 kilometers per second, approximately 38,000 miles per hour, underscores the vastness of cosmic scales. The probe has traveled approximately 160 astronomical units from Earth, approximately 24 billion kilometers, approximately 15 billion miles. This is a tiny fraction of the distance to the nearest star, Proxima Centauri, approximately 4.24 light-years, or approximately 268,000 astronomical units away. The universe's observable radius is approximately 47 billion light-years, approximately 4.4 times 10 to the 26 meters, approximately 2.9 times 10 to the 23 miles. These scales are relevant to the entropy argument. The observable universe contains approximately 10 to the 80 particles, each contributing to the entropy budget. The vastness of the cosmos does not weaken the thermodynamic argument. It strengthens it. A larger system reaches equilibrium more slowly, but given infinite time, it still reaches equilibrium. The fact that a system this vast has not reached equilibrium is even stronger evidence that the time elapsed has been finite. Now let us follow the evidence where it leads. Something has always existed. This is not faith, it is logic. If there were ever truly nothing, absolute nothing, with no energy, no fields, no laws, no space-time, no potential, then nothing would exist now. Nothing has no mechanism. Nothing has no capacity. Nothing has no tendency. 0 plus 0 equals 0. And it always equals 0, no matter how many times you add it. But we exist. The universe exists. The second law holds. The CMB radiates at 2.725 Kelvin. Galaxies recede at 67 to 68 kilometers per second per megaparsec. Stars burn hydrogen into helium. Black holes merge and radiate gravitational waves. Entropy is not at its maximum. Structure is not at its minimum. Something exists. Therefore, something has always existed. The universe itself has not always existed. The second law, the BGV theorem, the CMB, the observed disequilibrium, the Boltzmann brane argument, all confirm a finite past. The universe began approximately 13.8 billion years ago in a state of extraordinarily low entropy, a state with a probability of occurring by chance of approximately 1 in 10 to the power of 10 to the 123, as calculated by Roger Penrose. This beginning was not self-caused. Energy and matter are not conscious. They have no will, no agency, no ability to configure themselves into a state of such extraordinary specificity. They are effects, not causes. They require an external cause, a cause sufficient to produce the observed effect. Whatever caused the universe must possess specific attributes, attributes deducible from the evidence, not assumed by theology. First, externality. Whatever caused the universe must be external to the universe, because the universe, including its time, its space, its laws, and its entropy, had a beginning. The cause preceded the effect. The cause is not within the system it created, it is outside it. Second, eternality. Time began with the universe, or at the very least, our models of time break down at the Planck epoch, approximately 5.39 times 10 to the negative 44 seconds after the origin. Whatever caused the universe is not bound by time. It exists outside time, eternal in the sense of being beyond temporal succession, not in the sense of existing for infinite duration within time. The cause is not subject to the second law of thermodynamics, because the second law applies to physical systems within the universe, and the cause is external to the universe. Third, power. The cause brought a universe into existence, a universe with a mass-energy content of approximately 10 to the 70 joules, containing approximately 10 to the 80 particles, spanning approximately 94 billion light-years in diameter, with a Hubble expansion rate of approximately 67 to 68 kilometers per second per megaparsec. The power required to instantiate this system, from a state external to time and space, exceeds anything within the physical universe. Fourth, knowledge. The initial conditions of the universe are fine-tuned to a precision of 1 in 10 to the power of 10 to the 123. This is not a number that arises from randomness. This is a number that reflects selection, the specification of a particular, extraordinarily rare configuration from among an incomprehensibly vast space of alternatives. Selection of this precision requires knowledge of the alternatives, knowledge of what each configuration produces, knowledge of which configuration permits structure, stars, chemistry, and the conditions for complexity. This knowledge is not possessed by unconscious matter. It is not a property of energy. It is an attribute of mind. Fifth, will. A specific configuration was selected. Selection is an act. Acts require agents. The initial conditions could have been different, overwhelmingly different, by a factor of 10 to the power of 10 to the 123 to 1 against the observed state. The fact that one specific state was instantiated, the state that permits structure and complexity, implies that a choice was made. Choice requires a chooser. Will requires a being that possesses will. The cause is not a blind, undirected process. It is an agent with knowledge of the alternatives and the power to instantiate its choice. These are the attributes of a creator. Power, knowledge, will, eternality, externality, independence from the physical universe and its laws, including the second law of thermodynamics. These attributes are not imposed by theology. They are deduced from the evidence, from the second law, from the BGV theorem, from the fine-tuning of initial conditions, from the impossibility of an infinite past, from the observed disequilibrium of the cosmos. The chain of causes must terminate. The infinite regress argument, articulated by Aristotle, refined by Thomas Aquinas, championed in modern form by William Lane Craig through the Kalam cosmological argument, establishes that an infinite chain of dependent causes is logically impossible. If every cause requires a prior cause, stretching backward infinitely, then nothing would ever begin. An infinite regress has no first element. Without a first element, no subsequent element is possible. The fact that the present moment exists, the fact that we are here, now, observing a universe 13.8 billion years old, with entropy that has not yet reached its maximum, proves that the chain terminates. Something exists that is itself uncaused, eternal, self-sufficient, independent. This is the uncaused cause, the first cause, the foundation on which all dependent causes rest. The materialist may respond, perhaps matter or energy is the eternal, uncaused foundation. But this is precisely what the second law refutes. If matter and energy have existed for infinite time within a physical system, the second law requires that they have reached thermodynamic equilibrium. They have not. The universe is not in equilibrium. The entropy is not at its maximum. Stars shine. Structure exists. Free energy persists. Matter and energy, as they exist in the physical universe, have not existed for infinite time. They had a beginning, approximately 13.8 billion years ago. And the cause of that beginning is not itself a physical system subject to the second law. The cause is external, eternal, and independent, possessing the attributes we have deduced from the evidence. When I first understood this, that the most fundamental law in physics, applied to the most thorough observation in cosmology, leads to the conclusion that the universe had a beginning, and that the beginning requires a cause external to the physical universe, the materialist framework I had accepted as default became untenable. The evidence was not ambiguous. The logic was not optional. The second law, the BGV theorem, the fine-tuning of initial conditions, the Boltzmann brane paradox, each line of evidence converges on the same conclusion. The past is finite, the beginning was specific, and the specificity requires an explanation that transcends physics. The conclusion is not mysterious, it is rational. There is a creator. Let us now assemble the full evidence file, every datum, every equation, every experiment, every failed escape route, and state the conclusion plainly. The second law of thermodynamics, delta S greater than or equal to 0, is confirmed by every experiment in the history of physics. No exception has ever been observed. No machine has ever been built that violates it. No physical process has ever been measured that reverses it for a macroscopic system. The law is not a guideline. It is not a tendency. It is an absolute prohibition, grounded in the mathematics of probability, confirmed by the observations of 2 centuries, and applicable to every isolated system in the observable universe. Entropy, quantified by Boltzmann's formula S equals K sub B times the natural logarithm of W, always increases in isolated systems. The arrow of time, the unidirectional flow from past to future, from order to disorder, from low entropy to high entropy, is a consequence of the second law, applied to a universe that began in a low entropy state. The past hypothesis, the requirement that the universe began in an extraordinarily low entropy state, is not explained by any known physics. It is assumed as a boundary condition, the starting point from which all subsequent physics proceeds. David Albert formalized the term. Sean Carroll acknowledges the assumption. No equation derives it. Roger Penrose calculated the probability of this initial state occurring by chance at approximately 1 in 10 to the power of 10 to the 123, a number so large that it transcends human comprehension, mathematical notation, and every attempt at analogy. The initial conditions of the universe are not merely unlikely. They are specified, configured, with a precision that eliminates chance as a rational explanation. The heat-death argument, Lord Kelvin's 1852 observation, proves that an infinite past is thermodynamically impossible. If the universe had existed for infinite time, entropy would have reached its maximum. The universe would be in thermodynamic equilibrium. No stars, no galaxies, no temperature gradients, no free energy, no structure, no processes of any kind. A featureless, uniform void at a temperature indistinguishable from absolute zero, expanding endlessly into darkness, with no capacity for change, no potential for complexity, and no possibility for life. Imagine that. Imagine a cosmos with no light, no heat, no motion, no difference between one point and another. Nothing happening anywhere, ever. That is heat death. That is the destination of the second law. And if the past were infinite, we would already be there. We are not, though. The cosmic microwave background, discovered by Arno Penzias and Robert Wilson in 1965, confirmed by Kobe in 1992, refined by WMAP and Planck, radiates at 2.725 Kelvin, with anisotropies of 1 part in 100,000. Stars shine, approximately 200 billion galaxies in the observable universe, each containing hundreds of billions of stars, burning hydrogen into helium, fusing helium into carbon, forging the heavy elements of the periodic table in their cores and scattering them across interstellar space when they die as supernovae. The Sun, a G-type main sequence star, 1.989 times 10 to the 30 kilograms, approximately 4.4 times 10 to the 30 pounds, approximately 333,000 times the mass of the Earth, converts approximately 600 million tons of hydrogen into helium every second, at a core temperature of approximately 15 million Kelvin, approximately 27 million degrees Fahrenheit. It has been doing this for approximately 4.6 billion years. It will continue for approximately another 5 billion years. The Sun is not in thermodynamic equilibrium. It is a heat engine, converting nuclear binding energy into radiation, increasing entropy, moving the universe incrementally closer to heat death. The fact that this process is ongoing, the fact that the Sun has not yet exhausted its fuel, is direct evidence that the universe has existed for a finite time. The BGV theorem, proved by Borde-Guth-Vilenkin in 2003, closes the final escape route. Any space-time region with average expansion rate greater than 0 must be passed incomplete. It must have had a beginning. The theorem applies to inflationary models, to eternal inflation, to cyclic models embedded in expanding spacetimes, and to the multiverse. Guth himself, the inventor of inflation, is a co-author of the proof. The escape route through eternal expansion is closed by the physicist who opened the door to inflation. Every alternative model fails when confronted with the second law and the BGV theorem. The steady-state model, proposed by Bondi, Gold and Hoyle in 1948, is observationally falsified by the CMB and thermodynamically incoherent. An eternal, continuously creating universe would accumulate entropy without limit, reaching heat death despite continuous creation. The oscillating universe, analyzed by Tolman in 1934, accumulates entropy each cycle. Each successive cycle is larger, longer, and more disordered than the last. Infinite past cycles produce infinite entropy, heat death. The cycles have not been going on forever. There was a first cycle, a beginning. Modern cyclic models, Steinhardt-Turok ekpyrotic, Penrose's conformal cyclic cosmology, propose undemonstrated entropy reset mechanisms, ekpyrotic, or require unobserved proton decay and mathematical not physical conformal mappings, CCC. Neither explains the first cycle, neither derives the initial conditions, neither eliminates the need for a beginning. Eternal inflation and the multiverse, Lindy's eternal inflation, the string landscape, are passed incomplete by the BGV theorem. The multiverse has zero observational evidence, is unfalsifiable, and does not explain the laws governing the multiverse generating mechanism. The fine-tuning problem is not solved. It is multiplied. The quantum fluctuation hypothesis, the claim that the universe arose as a random vacuum fluctuation, fails the Boltzmann brain test. In an eternal equilibrium state, random fluctuations that produce isolated brains with false memories are overwhelmingly more probable than fluctuations that produce entire ordered universes. The fact that our observations are consistent with a real cosmic history, not with a momentary hallucination, eliminates the eternal fluctuation hypothesis. Science will eventually explain it is not an argument. It is faith in future discoveries deployed to avoid a present conclusion. The past hypothesis is a boundary condition, not a derivable result. No equation in physics generates the initial conditions from first principles. The question, why was the initial entropy so low, is the question physics starts from, not the question physics can answer. The observational evidence, Penzias and Wilson's 1965 CMB discovery, Kobe's 1992 black-body conformation and anisotropy detection, WMAP's precision cosmology, age 13.77 billion years, composition 5/27/68%, Planck's 2018 high-resolution data, omega sub tot equals 1.0007 plus or minus 0.0019, age 13.80 billion years, Hubble constant 67 to 68 kilometers per second per megaparsec, the 1998 supernova observations confirming accelerating expansion, the LHC's 2012 Higgs boson discovery at 125 giga-electron volts, LIGO's 2015 gravitational wave detection, Voyager 1's 2012 heliopause crossing, confirms a finite-age universe with specific, quantifiable, fine-tuned properties. Every datum is consistent with a universe that had a beginning and is evolving toward heat death. None is consistent with an infinite past. The equations tell the same story. Boltzmann's entropy formula, S equals K sub B ln W, quantifies the improbability of the initial state. The second law, delta S greater than or equal to 0, prohibits spontaneous reversal. The Friedmann equation, h squared equals 8 pi g over 3 rho minus k over a squared plus lambda over 3, governs the expansion that the BGV theorem proves must have had a beginning. The Bekenstein-Hawking entropy, S sub BH, equals K sub BC cubed A over 4 GH bar, shows that black holes dominate cosmic entropy, placing the universe firmly between its low entropy beginning and its high entropy end. Hubble's law, V equals H sub 0 D, describes the expansion, confirmed by every observation. The fine structure constant, alpha, approximately 1 over 137, determines electromagnetic strength at a value that permits chemistry and life. The Planck mass, m sub p equals the square root of h bar c over g, sets the natural mass scale whose ratio to the proton mass remains one of the deepest unexplained hierarchies in physics. The second law of thermodynamics, entropy, the arrow of time, the past hypothesis, the heat death, Boltzmann's formula, Kelvin's argument, Penrose's number, 1 in 10 to the power of 10 to the 123. The Borde-Guth-Vilenkin theorem, the Friedmann equation, the Hubble law, the Bekenstein-Hawking entropy, the CMB at 2.725 Kelvin, Kobe, WMAP, Planck, Penzias and Wilson, Guth, Vilenkin, Borde, Tolman, Eddington, Boltzmann, Kelvin, Penrose, Carroll, Albert. 13.8 billion years, 10 to the 104 in entropy units. The most fundamental law in physics, and it points one direction. The universe had a beginning. The past is finite. Infinite time is a logical fallacy, contradicted by the second law of thermodynamics, refuted by the Borde-Guth-Vilenkin theorem, eliminated by the Boltzmann brane paradox, and inconsistent with every observation of a cosmos that is manifestly not in thermodynamic equilibrium. The initial conditions were fine-tuned to a precision of 1 in 10 to the power of 10 to the 123, a number calculated by Roger Penrose, a secular physicist, a Nobel laureate, a man who does not draw the theistic conclusion, but whose data compels it nonetheless. No random process produced this. No cyclic model explains it. No multiverse eliminates it. No future physics can derive it. Because the question is not about dynamics within a framework, but about the existence of the framework itself. No equation within physics can explain why equations hold. No law within physics can explain why laws exist. The framework cannot account for itself. The explanation must come from outside. The evidence converges. The second law demands a beginning. The Borde-Guth-Vilenkin theorem proves a beginning. The CMB confirms a beginning. The Boltzmann brane paradox eliminates the alternative. The fine-tuning of initial conditions specifies the beginning to a precision that eliminates chance. Each line of evidence is independent. Each points in the same direction. When independent lines of evidence converge on the same conclusion, the probability of that conclusion being correct is not additive, it is multiplicative. The convergence is not coincidence, it is the signature of truth. Consider the full weight of what has been established. The universe began approximately 13.8 billion years ago in a state of extraordinarily low entropy. That state was not random. Its probability of occurring by chance is 1 in 10 to the power of 10 to the 123. The universe has been evolving since that beginning according to the second law of thermodynamics. Entropy increasing, order decreasing, free energy being consumed. The expansion of the universe, confirmed by Hubble in 1929, refined by WMAP and Planck, accelerated by dark energy, has been ongoing since the beginning and is proven by the BGV theorem to have had a definite start. Every alternative model that attempts to eliminate the beginning, steady state, cyclic, CCC, eternal inflation, multiverse, fails when confronted with the evidence. The escape routes are closed. The evidence demands a beginning. A beginning demands a beginner. The evidence points to an intelligent, powerful, eternal creator, one who exists outside time, outside the second law of thermodynamics, outside the physical universe and its laws. One who configured the initial conditions with a precision of 1 in 10 to the power of 10 to the 123, selecting from among an incomprehensibly vast landscape of alternatives the specific low-entropy state that permits stars, chemistry, structure, and the conditions for complexity. One who instantiated this configuration with power sufficient to bring a universe of 10 to the 70 joules into existence. One who possessed the knowledge to select the correct initial state and the will to choose it. Power, knowledge, will, eternality, independence from the created order. These attributes are not theological assumptions. They are deductions from the evidence, from the second law, from the BGV theorem, from the fine-tuning, from the impossibility of an infinite past. They are the attributes demanded by the data, and they are precisely the attributes that every civilization in human history has recognized in what they call God. The second law of thermodynamics is the most confirmed law in all of physics. It has no exceptions. It applies everywhere, always, without fail. And it points, with the weight of 2 centuries of confirmation behind it, to a beginning from which the arrow of time originates. A beginning whose initial conditions are fine-tuned beyond the reach of accident. A beginning that no natural process can explain, because every natural process operates within the framework that began at that point, and no framework can explain its own origin. This is the part that stays with me. Not the vastness of the numbers, though the numbers are vast. Not the elegance of the equations, though the equations are elegant. What stays with me is the convergence. Every line of evidence, thermodynamic, cosmological, observational, mathematical, philosophical, converges on the same point. The universe had a beginning, and the beginning was deliberate. The precision is not accidental. The laws are not self-generating. The initial conditions are not random. The convergence is not coincidence. The evidence, when examined honestly, leads one direction. And once you see it, once you follow the logic from Boltzmann's tombstone in Vienna to Penrose's calculation, to the BGV proof, to the CMB photons at 2.725 Kelvin, you cannot unsee it. The conclusion is not mysterious, it is rational. It is demanded by the evidence. There is a creator. That is not faith against evidence. That is the conclusion the evidence demands when examined honestly. That conclusion, once reached, changes everything. Good night.